Astronomers have just discovered a galaxy so distant that its light seems to pierce the primordial darkness. And this revelation raises questions unsettling enough to shake modern cosmology. MOM-Z14 emerges, like an ancient witness challenging everything we once believed. If this moment makes your heart shift gently in awe of the universe's vastness, share your perspective. And now, let us uncover why MOM-Z14 is startling the astronomical world. What if a single faint red speck at the edge of vision was enough to make us rewrite the story of the universe's first dawn? When astronomers speak in hushed voices about MOM-Z14, they are really speaking about that question, because this tiny galaxy lives so far away that its light began the journey toward us when the cosmos was still a newborn wrapped in darkness. According to our textbooks, such a world should barely exist. Yet here it is, shining back at us with a confidence that feels almost unsettling. As one researcher put it, looking at these early galaxies is like reading a chapter of the universe that we did not know was written yet. For decades before the year 2022, the furthest frontier of our sight was set by Hubble and a galaxy called GNZ11. It was already extraordinary, a whisper from a time less than 500 million years after the beginning. We thought we understood the rhythm of cosmic growth, the slow gathering of dark matter, the gentle birth of the first small galaxies, the long climb toward complexity. Then the James Webb Space Telescope opened its golden eye, tuned to the stretched red light of the ancient universe, and the script began to change. The discovery of Jade's GSZ14 was the first shock, but MOM-Z14 went even deeper in time, like a child of the first mornings shining far brighter than we had any right to expect. Why is MOM-Z14 so disturbing to our tidy theories? First, it is too far and therefore too early. Its redshift places it only a few 100 million years after the beginning, a moment when our models say the universe should still be assembling its first fragile structures. At that age, galaxies ought to be rare, small, dim, made mostly of pristine hydrogen and helium. Yet MOM-Z14 appears as a compact blaze of star formation, no more than about 500 light-years across, but crowded with newborn stars and enriched gas. One astronomer described these systems as little red embers scattered across the sky, glowing far more intensely than the early universe was supposed to allow. Then there is the question of age written in its chemistry. When we split the light of MOM-Z14 with a spectrograph, we do not see a simple baby cosmos. We see the fingerprints of nitrogen and other, heavier elements, the ashes of earlier generations of stars. To create those elements, massive stars must have lived, burned bright, and died in supernova explosions before MOM-Z14 gave off the light we detect today. That suggests that by this unbelievably early time, multiple cycles of birth and death had already unfolded in dense star-forming clouds. As another scientist remarked, the early universe seems to have hit the fast-forward button when we were not looking. There is also what we do not see. Many galaxies with furious star formation in the later universe appear to be anchored by supermassive black holes at their centers, engines that stir gas, regulate star birth, and shape the galaxy's evolution. In MOM-Z14, at least for now, we find no clear sign of such a giant lurking in the core. This absence may simply mean our instruments are not yet sensitive enough, but it also whispers a more provocative idea. Perhaps some of the earliest galaxies grew in ways that do not fit the simple story where black holes and galaxies rise together in lockstep. Before the era of Webb, we treated our models as if they were close to complete, especially for the broad strokes of structure formation. We knew the details would need polishing, but the overall picture felt secure. Now the sky is telling us a gentler, more humbling truth. The picture was never wrong in a crude sense, yet it was incomplete in ways that matter deeply. The abundance of bright, massive-looking galaxies at extreme redshift, including systems like MOM Z14, suggests that matter clumped faster, cooled more efficiently, or formed stars more vigorously than our equations predicted. Some astrophysicists speak of tweaking the recipes for dark matter, or the behavior of gas in tiny halos. Others wonder if something even more radical might be hiding in the data. For me, as a scientist who also loves the quiet poetry of the night sky, this is the real gift of MOM Z14. It reminds us that every model we build is a story we tell about reality, not reality itself. Before 2022, we had grown comfortable with a particular narrative about the cosmic dawn, a narrative born from Hubble's deep fields and computer simulations. Then a new telescope opened a deeper window, and the universe gently said, "You have glimpsed only the first verse of the song." In the words of Carl Sagan, science is not only a body of knowledge, it is a way of thinking. To think in this way is to accept that moments like the discovery of MOM Z14 are not threats to knowledge, but invitations to refine it. There is also a more personal lesson hidden in that tiny red smudge. We like to believe our timelines, whether in cosmology or in our own lives, are neat, ordered, predictable. First this, then that, one step after another. But reality often blossoms faster or slower than we expect. Just as galaxies in the early universe may have grown in sudden bursts of creativity, so too can understanding, wisdom, or change in a human life arrive earlier than we think we are ready, or later than we had hoped. The cosmos is reminding us that surprise is not a flaw in the pattern. It is part of the pattern itself. When you listen to the story of MOM Z14 with your eyes closed, you might imagine it as a distant lantern hanging in the first fog of time, casting a fragile glow across oceans of dark matter and cooling gas. That glow travels for billions of years, crosses expanding space, passes by uncounted galaxies that will one day host worlds and questions and beings like us. Finally, it reaches the mirror of a telescope parked far beyond the moon. And then, through screens and speakers, it reaches you. Between that infant galaxy and the person listening now, half asleep, perhaps, there is a thread of light and curiosity that ties the whole story together. So why does the discovery of MOM Z14 shake astronomy so deeply? Because it whispers that the universe was ready to create complexity long before we thought. Because it shows that our most confident assumptions can age and fall away in a single observing run. Because it proves once more that the cosmos is not obligated to match the maps we draw of it. And the lesson we can draw, in science and in life, is simple and yet endlessly demanding. Stay curious. Hold your ideas gently, and be willing to be surprised by reality. Somewhere at the edge of our vision, a tiny red galaxy is still shining, patiently waiting for us to learn how to read its message more clearly. What if everything we thought was the cosmic horizon was only the first soft whisper of a universe much deeper than our eyes had ever reached? When Hubble stretched its gaze and touched the faint glow of GNZ 11, it stood like a lone traveler at the edge of an ancient map, murmuring that beyond this trembling boundary something older, quieter, still waited in the dark. GNZ 11 became the emblem of that limit, a tiny galaxy shimmering at the threshold of what a 2-4-meter mirror and visible light vision could ever hope to see. But the universe did not end there. Light from earlier epochs continued drifting toward us, stretched thinner and colder by the relentless expansion of space-time, slipping out of the colors Hubble could feel. Hubble was a brilliant painter given only half a palette, able to trace marvels, yet unable to reach the wavelengths where the oldest stories hid. That is why its journey stopped at GNZ 11, not because nothing lay beyond, but because the universe had shifted its language into infrared. And then JWST arrived, a new kind of eye, calm and gold and wide as a cosmic sunrise. Its 6-5-meter mirror unfolded like a celestial lotus, gathering every trembling photon that time had thinned across billions of years. Tuned entirely to infrared, JWST stepped into the silence where ancient galaxies whispered their names, names Hubble could never hear. Infrared is the archaeology of the universe, astronomer John Mather once said, and with JWST he turned that sentence into a doorway leading backward through time. Suddenly the darkness brightened, not with new stars, but with revelations already on their way toward us since the cosmic dawn. MOMZ-14 emerged first. Then others followed like a chain of forgotten lanterns, lighting up the night before creation took shape. These galaxies were smaller, faster, fiercer than we predicted. Their light reached us not as the timid glow of newborn worlds, but as the confident blaze of systems that had already lived many lives. As Brian Cox once said, "Every time we build a better telescope, the universe surprises us." And JWST seemed built precisely for those surprises. The transition from Hubble to JWST was not a replacement, but an awakening. Hubble mapped what we could see. JWST maps what we can finally understand. Between them lies a bridge woven from patience, physics, and the quiet human longing to know where the first light came from. The deeper JWST peers, the more our early assumptions soften, dissolve, open into new questions about how quickly galaxies formed, how early stars died, and why the cosmos seems far more ambitious than our models predicted. And as we drift with this golden telescope through the dim corridors of time, there is a gentle comfort in knowing that discovery is a shared pilgrimage, a collective breath of curiosity carried across continents and screens. If this journey of sight and wonder speaks to you, let your voice join the constellation of thoughts below. Like, subscribe, and help keep this quiet voyage moving forward. Because the story does not end here. It leads us deeper into the mystery of MOMZ-14 and the cosmic tremor it has awakened. What if the color of light itself was a secret code from the beginning of time? What if every stretched wavelength was a whisper from a younger universe, telling us how far we have drifted from our own cosmic birth? When astronomers say MOMZ-14 has a redshift of 14.44, they are not just reciting a number. They are reading a date written in the language of light. Redshift sounds technical, but at its heart it is a very human idea. Imagine a song being played on an old record player, and as the universe expands, the record itself is being stretched under your hands. Every note becomes lower, every sound more drawn out. That is what happens to light crossing an expanding cosmos. Its waves are pulled longer. Its color slides from blue to red, from youthful brightness to ancient ember. As space itself swells over billions of years, the photons keep traveling, but the road beneath them is being stretched, and so they arrive to us tired, cooled, shifted toward red. Edwin Hubble once remarked that the farther a galaxy is, the faster it seems to be rushing away from us. That simple observation became the backbone of modern cosmology, because it taught us that distance and time and color are all woven together. Higher redshift means greater distance, and greater distance means deeper into the past. So when we speak of redshift 14.44, we are staring down a corridor of time to an era when the universe was only a few 100 million years old. A child still rubbing the sleep of the Big Bang from its eyes. The reason stretched light is older is not magic. It is geometry. In a static universe, a photon would simply cross space like a bullet through still air. But our universe is not still. It is more like an ocean tide forever rising. As the space between galaxies swells, so too does the wavelength of the light inside it. Like a pattern painted on a balloon, you are slowly inflating. By the time that photon brushes the mirrors of the James Webb Space Telescope, it carries the imprint of every moment of expansion it has survived. The more expansion, the greater the stretch, the higher the redshift. Physicist Brian Cox likes to say that when we look out into the night sky, we are not seeing the universe as it is, but as it was. Redshift is the ruler that lets us measure how far back that was. But how does JWST actually turn this ghostly redness into a precise number like 14.44? Here, the poetry of light meets the precision of instrumentation. Webb is not just a camera. It is also a spectrograph. It takes the light from MOM-Z14, spreads it into a rainbow, and inspects it line by line. Atoms and ions in stars and gas clouds leave sharp fingerprints in that rainbow, thin, bright or dark lines at very specific wavelengths. In a laboratory on Earth, those fingerprints sit at known positions. Hydrogen speaks at one set of wavelengths, oxygen at another, nitrogen at another. In MOM-Z14, those same patterns are still there, but they have been pushed far toward the infrared, like familiar songs played in an impossibly lower key. By measuring how far each line has shifted compared to its laboratory value, astronomers calculate the redshift with astonishing accuracy. It is as if JWST listens to the spectrum and says, "This is hydrogen, but it has been slowed and stretched by exactly this much. Therefore the galaxy must sit at this cosmic distance and this cosmic age." Jim Peebles, one of the architects of modern cosmology, has often emphasized that the universe leaves us a remarkably consistent story in its light, if only we learn to read it correctly. Redshift 14.44 is one of those lines in the story where the plot suddenly twists. Because at that redshift, the cosmos should still be groping its way out of the dark ages. Gas just beginning to clump, the first fragile stars flickering on. Yet MOM-Z14 appears bright, vigorous, chemically complex. It shines like a bustling city appearing on a map from a time when only tiny villages were supposed to exist. That is why this number matters so much. It is not just the distance that is troubling. It is what we find when we get there. The flow from the concept to the observation is almost meditative. We start with the idea that space expands. We watch light stretch as it travels. We let a telescope in a cold Lagrange point listen to that stretched light. And from these delicate measurements, we are forced to rethink how quickly matter gathered, how urgently stars were born, how early galaxies like MOM Z14 grew up. Neil deGrasse Tyson likes to remind us that the universe is under no obligation to make sense to us. Redshift 14.44 is the universe politely clearing its throat and saying, "You may need to adjust your expectations." For some watching this story unfold, the numbers can feel abstract. But there is a quiet way to sit with them, almost like a cosmic meditation. You can imagine each extra unit of redshift as another layer of distance, another veil of time lifting away. At redshift of 1, we see a universe already in its middle age. At 10, we are almost at the threshold of first light. At 14.44, we are so close to the beginning that our usual intuitions no longer hold. Galaxies are not supposed to have had enough time to grow so bright, to forge heavy elements, to host such intense star formation. And yet, their MOM Z14 is shimmering like a distant lantern at the edge of what our theories considered possible. In moments like this, it is worth remembering Carl Sagan's gentle thought that we are a way for the cosmos to know itself. When we measure the redshift of MOM Z14, the universe is in a sense measuring its own childhood through our instruments. Our curiosity, our telescopes, our equations are how the cosmos looks back on its first fragile dawn. If that idea moves you even a little, if the notion that a single number like 14.44 can peel back billions of years makes you want to follow this story to its end, then you are already part of this grand experiment. Let your questions live with ours. Let your wonder sit beside the data. And if you wish to keep walking down this quiet path through expanding space with us, listening to more of these distant lights and the secrets they carry, you can stay close to this channel. Add your voice in the comments, whisper your own theories, and gently tap subscribe so that each new shard of ancient light finds its way back to you. Because somewhere beyond our telescopes, the next redshift is already on its way, carrying another question from the deep past. Why would a tiny island of stars only 500 light-years across shine like a lighthouse at the edge of time, while the young universe around it is supposed to be quiet and dim? When we look toward MOM Z14, we are not supposed to see a blaze. We are supposed to see a faint ember, a small cloud of newborn stars still struggling to ignite in a cosmos barely awakened from the dark ages. Standard pictures tell us that in those first few 100 million years after the great beginning, matter was fragile. Gravity was only starting to gather gas into clumps, and galaxies should have been simple and shy, made mostly of hydrogen and helium, with just a few timid stars quietly flickering in the fog of reionization. Yet MOM Z14 looks nothing like that. It glows like a crowded city at midnight, packed into a town the size of a single bright knot in one of our galactic nebulae. In our Milky Way, the distance from one edge to the other stretches more than 100,000 light-years, a sprawling spiral of stars, gas, and dark matter. But MOM Z14 squeezes its light into a space 200 times smaller and still outshines almost everything around it at that epoch. Astronomers expected early galaxies to be like small villages scattered across a vast wilderness. But this one behaves like a metropolis built overnight. That is where the unease begins. In the frameworks that have guided cosmology for decades, small structures grow slowly. Star formation is gradual, and complexity takes time. As the astrophysicist James Peebles once reflected, the success of modern cosmology rests on the idea that structure emerges gently from small beginnings. MOM-Z14 does not feel gentle at all. It feels explosive. To understand this, we imagine gas in the young cosmos like a great silent ocean, mostly smooth, disturbed only by tiny ripples from quantum fluctuations stretched by inflation. Over time, gravity deepens some of those ripples into basins where gas can fall cool and form stars. But that process should be slow, because the universe is expanding, trying to pull everything apart as gravity pulls locally together. So why is this galaxy so bright when its clock has barely started ticking? One possibility is that the gas feeding MOM-Z14 collapsed with unusual speed into an extraordinarily dense core. A cosmic pressure cooker where star formation cannot help but run wild. In such an environment, giant molecular clouds would crowd together. Supernovae would erupt in rapid succession, and shock waves would compress even more gas into new stars. The result is a starburst, a brief and furious phase when a galaxy converts its gas into stars, far faster than the quiet spiral we live in today. Astronomers think we might be catching MOM-Z14 right in the middle of such a storm. Its brightness could be the signature of thousands or millions of hot young stars, burning blue-white, pouring out ultraviolet light that has been stretched by the expansion of the universe into the infrared bands that the James Webb Space Telescope can see. As Carl Sagan used to remind us, stars are the engines that light the sky and forge the elements of worlds. In a place like MOM-Z14, those engines are running at full throttle. But brightness alone is not the whole story. When scientists dissected the light of this galaxy with a spectrograph, they found hints of nitrogen in surprising abundance, a whisper that multiple generations of stars may already have lived and died there. Nitrogen is not born in the first simple stars. It is crafted in their cores and released when those stars shed their outer layers or explode as supernovae. To see such chemical richness so early suggests that star formation in that region began even earlier than the moment we are now observing, like hearing the echo of a song that started before the curtain rose. Theoretical models must stretch to accommodate this. Either the first stars formed astonishingly quickly after the cosmic dark ages lifted, or gravity gathered matter into rare but very dense knots, where the cycle of birth and death accelerated. Brian Cox once said that the universe is not only stranger than we imagine, it is stranger than we can imagine. MOM-Z14 seems to embody that thought. A small jewel of light that does not behave according to the comfortable timelines drawn in our textbooks. There is another twist that deepens the riddle. In many galaxies with intense star formation, we find a supermassive black hole at the center. Its gravity stirring the gas, its radiation sometimes regulating how fast new stars are born. Yet in MOM-Z14, there is no clear sign of such a giant anchor. It is as if a city were ablaze with life, but had no central power plant. That absence suggests that at least some galaxies can ignite spectacular bursts of star formation without the guiding hand of a central black hole. Or perhaps that any black hole present is still small, faint, or buried in dust beyond our current ability to see. This challenges the neat narrative in which galaxies and their central black holes grow hand in hand from the very beginning. Instead, the dance may start offbeat, with stars surging first and black holes catching up later. Michio Kaku has remarked that every time we build a more powerful telescope, we are forced to rewrite the book of the cosmos. The James Webb Telescope is proving that point relentlessly, and MOM-Z14 is one of the sharpest edits so far. Our expectations of dim, smooth infant galaxies give way to scenes of frantic activity compressed into tiny volumes of space, like campfires flaring suddenly in a night we thought was empty. Perhaps there is a selection effect at work. We see the brightest and most extreme objects first because those are easiest to detect. And somewhere in the background there may still be countless faint, quiet galaxies exactly like the ones our models predicted. But even if that is true, the existence of objects like MOM-Z14 tells us that the menu of possibilities in the early universe is richer than we assumed. The cosmos is not obligated to behave in the most average way. It only needs to obey its fundamental laws. And those laws, when applied to initial conditions we do not fully know, can produce rare, intense outliers that surprise us. In the soft darkness of intergalactic space, this little galaxy shines like a bell being struck again and again by the hammer of gravity, sending ripples of starlight across billions of years until they reach our instruments. When you contemplate that glow, you are watching youth at its most reckless. A universe barely a fraction of its current age already experimenting with rapid complexity. The meditative part of this story is simple yet profound. Our theories are not the sky. They are only lanterns we hold up as we walk under it. MOM-Z14 is one of those moments when the sky gently takes the lantern from our hand and tilts it in a new direction, inviting us to see that even in the smallest places at the earliest times the universe may be more eager, more creative, and more restless than we dared to imagine. What does it mean when a young galaxy burns with ancient light, yet seems to lack the dark heart we expect at its center, in the quiet after the data download? Astronomers stare at the spectrum of MOM-Z14 and realize something unsettling. Where they thought they would find the unmistakable signature of a supermassive black hole, a gravitational monarch sitting in the core and feeding on gas and stars, they find instead a strange absence. A galaxy only about 500 light-years across, blazing with newborn stars, yet no roaring engine at its heart. For decades, the story seemed simple enough. Galaxies and supermassive black holes grow together like a tree and its roots, each shaping the other. In the nearby universe, we almost always see this partnership. From quiet spirals to furious quasars, the mass of the central black hole tracks the mass of the surrounding stellar bulge so well that it became almost a law of nature in our models. We imagined the early universe as a place where tiny seeds of black holes formed quickly, then helped regulate star formation by heating and stirring the surrounding gas. Yet MOM-Z14 whispers a different possibility, that at least some galaxies may experience a wild childhood, before any central giant settles in. When we say this galaxy appears to lack a supermassive black hole, we are also confessing that our expectations were built from a later, calmer universe. In our simulations, we tend to weave black holes into the story very early, because they help make the equations behave. They prevent gas from collapsing too efficiently. They keep galaxies from becoming unrealistically bloated with stars. But here is a real object that seems to do exactly that. Form stars at a furious rate without the breaking power of a central abyss. As the physicist Subramanian Chandrasekhar once reflected, the universe is not only stranger than we imagine, it is stranger than we can imagine. MOM-Z14 feels like an echo of that thought made visible. Perhaps black holes in some regions formed later, or in a different way. Or perhaps a smaller black hole hides there, too faint for our current instruments to see. Whatever the answer, this tiny galaxy quietly tells us that the neat co-evolution story between galaxies and their central giants is at best incomplete. Then, there is the chemistry, which may be even more shocking than the missing black hole. When astronomers spread the light of MOMZ-14 into its spectral rainbow, they find strong hints of nitrogen and other heavier elements, what astrophysicists collectively call metals. In the earliest times after the Big Bang, the universe was almost pure hydrogen and helium, a pale and simple gas. Every carbon atom in your body, every oxygen atom in your lungs, every iron atom in your blood had to be forged later in the cores of stars and scattered by their deaths. That is why Carl Sagan could say we are made of star stuff. But MOMZ-14 appears in an era when the universe was still incredibly young, and yet its gas is already enriched, already seasoned with the ashes of previous stellar generations. Nitrogen does not appear in abundance overnight. It is often tied to stars that live long enough to process lighter elements in their interiors before gently returning that material to space through stellar winds or more violent deaths. For MOMZ-14 to show strong nitrogen signatures, something extraordinary must have happened quickly. Either massive stars formed in extreme densities and cycled material with ruthless efficiency, or there were already earlier waves of star formation in some even more primitive structures that merged to build this galaxy. The presence of these metals is like finding old footsteps in what you thought was untouched snow. It implies that before the light of MOMZ-14 ever set out across the cosmos, other stars had already blazed and died, seeding their surroundings with the ingredients for future worlds. As Brian Cox likes to remind us, every one of us is at least in part the product of stars that lived and died before the sun existed. MOMZ-14 seems to extend that intuition backward, to a time almost uncomfortably close to the cosmic dawn. This is why astronomers say the galaxy feels old and young at the same time. Young in size, in its furious starburst activity, in its compact body no larger than a bright knot in one of our own spiral arms, yet old in chemical memory, carrying the fingerprints of stars that must have come and gone in cycles we did not think the early universe had time to sustain. The usual picture painted in textbooks shows a slow enrichment. Galaxies starting simple and gradually becoming more metal-rich as time flows forward. MOMZ-14 instead suggests pockets of the cosmos where evolution may have run in fast forward, where gravity and gas and radiation conspired to build and destroy stars in rapid succession. If that is true, then our models of galaxy formation are like sketches of a landscape seen from a great distance, graceful but missing the intricate textures of the real terrain. There is also a deeper philosophical unease beneath the technical puzzles. For decades we have comforted ourselves with the idea that if our equations are elegant enough, and our simulations high resolution enough, the universe will conform. Yet again and again instruments like JWST remind us that the cosmos is not obliged to respect the limits of our imagination. It only plays by its own laws. As the theorist John Wheeler once wrote, "We are no longer satisfied to understand the universe. We want the universe to understand us." Staring at this small, bright, chemically rich galaxy without a clear central black hole, you can feel that tension. Are we discovering the true diversity of galactic childhoods? Or are we confronting the edges of a theory that worked beautifully for the Middle Ages of the cosmos, but falters at its dawn? In the softer hours of the night, when the raw plots and error bars are set aside, MOMS of 14 becomes something more than a data point. It is a small lamp hanging in the distant dark, carrying within its light stories of lives and deaths we did not expect to find so early, and hinting at gravitational dramas that perhaps do not always require a supermassive tyrant at the center to unfold. It invites us to imagine a universe where some galaxies grow like wild gardens before any single trunk dominates, where metals spread like whispered rumors through crowded stellar nurseries. In that sense, this galaxy is doing what the best scientific discoveries always do, not closing a chapter but opening a deeper question. How many more objects like this are waiting just beyond our current reach? And what will happen to our cherished models when hundreds of such outliers are no longer exceptions, but part of a new cosmic pattern? So as we listen to the faint light of MOMS Z14 arrive after more than 13 billion years of travel, we are also listening to our own assumptions, cracking and reforming. Perhaps supermassive black holes are not universal midwives of galaxy growth. Perhaps chemical maturity can emerge in startlingly short timescales. Perhaps the young universe was a more chaotic and inventive artist than we thought. In the end, this tiny galaxy at the edge of our vision reminds us of something simple and humbling. The cosmos is still in the process of telling its story, and through instruments like JWST, we are just beginning to hear the older verses beneath the melody we thought we knew. What if the first lights of the cosmos were never meant to be faint whispers, but blazing cries that echo across the newborn universe? When astronomers turned JWST toward the deep sky, they did not find a quiet darkness waiting to be slowly filled with stars. They found an unexpected swarm of ancient galaxies glowing fiercely, the so-called little red dots. Their presence is a question, a challenge, a gentle rebellion against the stories we once thought were settled. According to earlier models, the early universe should have been a calm and primitive place. Small galaxies gathering matter shyly, lighting their first stars with modest energy. Yet JWST reveals something else entirely. A cosmic dawn crowded with luminous sparks. Tiny galaxies burning with an intensity that feels almost impatient. Astronomer Brian Cox once said that the universe is not only stranger than we imagine, but stranger than we can imagine. Little red dots embody that sentiment perfectly, each one an ember that refuses to fit inside our theoretical boxes. These galaxies are minuscule compared to the Milky Way, only a few hundred or thousand light years across, yet they shine with the brightness of giants. Their red glow tells us they are ancient. Their intensity tells us they are full of new stars. And their chemical fingerprints whisper of multiple generations of stellar birth and death. To forge elements, beyond hydrogen and helium, stars must live, burn, collapse, and scatter their ashes, meaning the universe must have begun this cycle far earlier than expected. The mystery deepens because these galaxies are not rare accidents. They appear in surprising numbers across JWST's deep fields. For years, astronomers assumed such objects existed at the statistical edges, precious anomalies, cosmic outliers. Instead, JWST paints a dawn sky where the extraordinary is common. This forces us to ask whether our pre-JWST models truly misjudged the pace of structure formation, or whether the early universe contained physical processes we have yet to recognize. As Richard Feynman said, science is the organized skepticism of our own understanding. And here, skepticism becomes starlight. Each little red dot posing a question against the dark canvas of space. Some scientists argue that our models are not broken, only incomplete. Like early sketches awaiting the detail that transforms a drawing into a landscape. JWST is adding those missing strokes, revealing that the universe's first billion years were not a quiet prelude, but a feverish eruption of galactic creativity. The data arrive like waves, reshaping the shores of theory. Others propose more radical possibilities, that star formation in dense primordial regions may have been far more efficient than expected, or that dark matter itself may behave differently in the early cosmos. These ideas are not conclusions, but invitations to look again. And so the little red dots linger in our thoughts, not as puzzles to be solved quickly, but as meditative sparks reminding us that the universe began with urgency, intensity, and a strange beauty we are only now beginning to sense. In their glow, we glimpse a cosmos more restless than we imagined. A cosmos that keeps rewriting its first chapter just as we learn how to read it. What happens when a galaxy emerges from the darkness of the early cosmos with such brilliance and complexity that it seems to whisper secrets we were never meant to hear? This is not a question from science fiction, but from the front lines of astronomy itself. The discovery of MOM-Z14 has ignited not just curiosity, but quiet alarm among cosmologists who have long relied on the LCDM model, the so-called standard model of cosmology, to explain the unfolding of the universe since the Big Bang. But MOM-Z14 is not unfolding according to the script. It is defiant, dazzling, and disturbingly early. According to the LCDM model, the universe began as a nearly uniform sea of matter and energy, slowly forming structure over billions of years. Galaxies were expected to grow gradually through mergers and cooling gas clouds, lighting up gently with stars as time moved forward. The early universe should have been dim and simple, a quiet prelude to the cosmic symphony that would follow. As Dr. Wendy Friedman once noted, the early universe was supposed to be a sleepy place. But MOM-Z14 is not sleepy, it is blazing. Discovered by the James Webb Space Telescope in a patch of ancient sky where darkness was expected. MOM-Z14 appeared with a redshift of 14.44, meaning we see it as it was just a few 100 million years after the Big Bang. And yet, in that impossibly early time, this galaxy is bursting with newborn stars, glowing more brightly than it should, as if time itself had been condensed in its core. It is not vast like the Milky Way, but within its tiny body lies a fury of creation that challenges the idea of slow galactic evolution. Dr. Brant Robertson of UC Santa Cruz remarked, "We expected galaxies this early to be faint and rare, not luminous and numerous." But MOM-Z14 stands against that expectation like a torch held up to a centuries-old map that no longer matches the terrain. Its richness in nitrogen hints that stars have lived and died before it, generations already born and gone in the blink of cosmic time. This alone should not have been possible, and yet it is. The LCDM model has never claimed to be perfect, but it has been profoundly successful at predicting cosmic microwave background patterns, large-scale structure formation, and the accelerating expansion of space itself. It has become the framework of modern cosmology, guiding thousands of studies across decades. To now encounter galaxies like MOM-Z14 that are too bright, too chemically complex, and perhaps too numerous for this model is to sense the ground shifting beneath the edifice of cosmological theory. It may not be that LCDM is wrong, but that it is incomplete. Just as Newtonian mechanics gave way to general relativity without being discarded entirely, the current model may be whispering its own limits through the quiet defiance of galaxies like MOMZ14. As Dr. Priyamvada Natarajan has suggested, the universe doesn't lie, but it sometimes hides. Perhaps these early galaxies are not anomalies but messages from epochs we barely understand, that the rules are broader than we imagined. The emotional weight of this is not just scientific, but existential. We live in a universe that once seemed to obey order, unfolding like a story told slowly over eons. But now, the story appears more like a poem written in a language we are just beginning to translate. What else lies hidden behind that veil of ancient light? What truths pulse in the red glow of galaxies long gone? And if our models need to evolve, perhaps so do we. Because each time the cosmos surprises us, it is not simply revealing new objects in the sky, it is offering a deeper view of ourselves. MOMZ14 may be the first of many such revelations to come. Galaxies that reach across time to hand us a key we did not know we were missing. A key that may unlock not only the structure of the universe, but the nature of beginnings themselves. Keep watching the stars, for they are writing a story far older than memory and perhaps far stranger than any dream. What if the most mysterious galaxies are not rare exceptions, but only the beginning of what we are meant to see? Somewhere beyond the veil of ancient light, far past the echoes of the first stars, a new eye is preparing to open, a mirror not of glass, but of time itself. The Nancy Grace Roman Space Telescope, often called the wide-eyed cousin of JWST, is poised to gaze not into a single corner of the sky, but across vast cosmic fields with unprecedented depth and detail. While the James Webb has stunned the world by revealing galaxies like MOMZ14 compact, bright, and shockingly evolved, just a few 100 million years after the Big Bang, Roman may unveil not just one or two more of these strange entities, but hundreds or even thousands. And with them, a silent storm of questions will awaken. When we look far into the cosmos, we're also looking back in time, said Dr. John Mather, Nobel laureate and senior project scientist for JWST. The universe is still whispering its story to us through light that began its journey billions of years ago. Roman's mission is to catch those whispers not as faint traces, but as a grand symphony spread across the sky. Unlike the tunnel vision precision of Webb, Roman's strength lies in its sweeping gaze, the ability to capture large-scale patterns and uncover entire populations of early galaxies that have so far eluded us. It will not merely deepen our understanding of a few isolated cases. It will reveal the cosmic context that binds them. The discovery of MOMZ14 has already sent shockwaves through the scientific community. A galaxy so small yet so bright, so chemically mature yet so ancient, and formed in an era where such complexity was never expected. It defies the prevailing models that paint early galaxies as quiet cradles of dust and hydrogen. Instead, MOMZ14 pulses with fierce star formation, a rapid heartbeat in the youth of the universe. And if MOMZ14 exists, it implies that others like it must exist too, hidden in the darkness, waiting for our instruments to evolve. This is where Roman enters not as a replacement for Webb, but as its wide-field counterpart, its cosmic cartographer. Its surveys will stretch across expanses of sky that Webb can only touch in fragments, mapping out where galaxies cluster, how they grow, and whether these enigmatic early galaxies are scattered anomalies or the tip of a buried iceberg. Roman will give us the statistical power to answer the big questions, says Dr. Jane Rigby, an astrophysicist at NASA Goddard. How common are these galaxies? How fast did they really form? Are we missing something fundamental about the first billion years? The possibility is thrilling and troubling. If Roman finds that galaxies like MOMZ14 are not just frequent but dominant in the early epochs, then the quiet, gradual evolution we once believed in must be rewritten. Perhaps the early universe was not a dim dawn, but a blinding sunrise. Perhaps stars bloomed not in whispers but in shouts, and gravity shaped worlds in fast forward. Such a revelation would demand more than new models, it would demand a new story about our cosmic origins. Yet even as Roman prepares to launch, the questions multiply. Will it find the first true giants of the universe, proto-galaxies stretching across thousands of light years, already forming structure when time had barely begun? Will it trace the web of dark matter that cradled those first luminous nodes? Will it reveal galaxies with no known analogues, beacons not of what we expect, but of what we can't yet imagine? The great irony is that the farther we look back, the more restless the present becomes. Every time we extend our reach, the past shifts under our feet. Momsy 14 is a reminder of that instability, a luminous question mark flickering in the night. And Roman, with its unblinking gaze, may turn that question mark into an exclamation or into a doorway. In the vast silence between galaxies, there is a kind of music waiting to be heard. Roman's task is to listen for its first notes, not to confirm what we know, but to challenge it. Not to explain the familiar, but to illuminate the unknown. If the early universe is more vibrant, more chaotic, more alive than we ever dared believe, then every new galaxy will be like a memory returned from cosmic amnesia. Perhaps the history of the universe is not a slow unfolding, but a cascade of forgotten fire. And Roman, like a lighthouse turned backward in time, may help us see not just where we came from, but what we've yet to remember. What if the universe wasn't as random as we believed? What if across the incomprehensible gulf of cosmic space, galaxies ancient and immense were silently conspiring to turn the same way? This strange alignment, discovered not in the fevered dreams of a science fiction writer but in cold astronomical data, has opened a door to one of the most haunting questions in modern cosmology. Does the universe have a preferred direction? In a universe born from chaos, shaped by chance, and governed by the impartiality of physical laws, one would expect the spin of galaxies to be scattered evenly in all directions. Like leaves on a restless pond, some should spiral left, others right, their dance dictated by local fluctuations and primordial turbulence. But that's not what we're seeing. Recent observations suggest a perplexing pattern, a subtle yet consistent bias in the rotation of galaxies over vast swaths of space. Instead of randomness, there's rhythm. Instead of chaos, a whisper of order. And this whisper is growing louder with every new survey. This could be the hint of a dunned cosmic axis, remarked Dr. Lior Shamir of Kansas State University. It challenges the very principle that the universe is isotropic, the idea that there is no special direction in space. The isotropy principle has long been a cornerstone of the standard model of cosmology. It assures us that no matter where we look, the universe should appear roughly the same in all directions. But the spin alignment calls this into question. Imagine galaxies not as solitary wanderers but as dancers in a vast ballet. Their motions subtly synchronized across distances too great to fathom. Such a choreography would be almost impossible under our current understanding unless something deeper was at play. Something written into the fabric of space-time itself. Some researchers have speculated that this directional preference could be a relic of initial conditions imprinted at or before the Big Bang. Others suggest it may point toward physics beyond the known, perhaps related to dark energy, cosmic inflation, or even torsion in the very geometry of the universe. If confirmed, this could be a signature of new physics, said Professor Niayesh Afshordi of Perimeter Institute. What makes this even more unsettling is the scale at which the effect appears to manifest. These are not local phenomena, like swirling storms in a planetary atmosphere. These are tendencies observed across hundreds of millions of light-years. Grand structures of cosmic architecture leaning ever so slightly in a unified direction. It's like discovering a faint breeze moving through a cathedral of stars. Is it possible that what we call random is simply misunderstood order? That the spin, bias is not an anomaly but a message, a relic of a cosmic memory etched in motion. There is a quiet elegance in such an idea, where the oldest galaxies are not only witnesses to time but storytellers through their spiral arms. Yet skepticism remains vital. Scientists caution that observational bias, sampling errors, or even limitations in data processing could mimic such patterns. The universe, after all, is a master of illusion. But with each new instrument, from the James Webb Space Telescope to the upcoming Nancy Grace Roman telescope, the fog thins, and the possibility sharpens. Should the alignment persist under deeper scrutiny, it might suggest that the universe was born not from absolute chaos, but from a blueprint of subtle asymmetry. A twist encoded into space-time at the moment of creation. Could it be that beneath the veil of cosmic noise, there lies a hidden order, not imposed, but intrinsic? Carl Sagan once said, "Somewhere, something incredible is waiting to be known." Perhaps that something is not hidden in distant galaxies but in how they spin, slowly, silently, faithfully carrying the story of the cosmos on their arms. And so the question lingers like starlight, soft, persistent, impossible to ignore. Does the universe have a preferred direction, or are we just beginning to see the faint outlines of a greater truth? Let your curiosity turn as galaxies do, not towards certainty, but into the depths of wonder. What if the Big Bang was not the beginning of everything, but the aftermath of something else collapsing? This question has haunted physicists and philosophers alike, a whisper in the dark halls of cosmology that refuses to fade. Could our universe be cradled inside a black hole? Not metaphorically, but literally enclosed within the event horizon of a far larger cosmos. A parent universe whose own death gave birth to ours. The idea sounds fantastical at first blush, yet in the delicate tapestry of theoretical physics it emerges not as fiction but as a possibility. One that redefines our origin story and the architecture of reality itself. Nobel laureate Roger Penrose once remarked, "The Big Bang may have been just one aeon in an eternal sequence of cosmological cycles." And physicist Nikodem Popowski takes this notion further with what's called black hole cosmology. The hypothesis that every black hole might spawn a new universe on the other side of its singularity. In this view, the Big Bang was not an explosion from nothingness but a transformation, a rebound, from a gravitational collapse in another realm. To understand this, we must listen closely to the silence of the void. In the final stages of a massive star's life, when its own mass overcomes all known forces, it collapses under its weight into a singularity, a point of infinite density wrapped inside an event horizon. According to general relativity, nothing escapes this boundary. Not light, not time, not information. But what if that singularity is not the end, but a bridge? Instead of collapsing into a dimensionless point, some extensions of Einstein's theory, such as Einstein-Cartan theory, suggest that space-time has a property called torsion, a kind of intrinsic twist that resists infinite compression. At extreme densities, this torsion could create a repulsive force strong enough to halt collapse and trigger a bounce. What follows is a rapid outward expansion, not within the old universe, but into a newly budding one on the other side of the black hole wall. What we call the Big Bang might be such a big bounce, the echo of another cosmos giving birth to our own. This raises an extraordinary implication. Every black hole in our universe could be a seed of creation, a cosmic womb, nurturing a child universe we can never see from the outside. In turn, our own universe may be the interior of one such black hole, born from the death of a star in another vast reality. The symmetry of this vision is breathtaking. Collapse and expansion become two sides of one cosmic rhythm. Creation is no longer a singular miracle, but an endless generative dance. A multiverse, not of parallel lines, but of nested spheres. Lee Smolin, theoretical physicist and author of The Life of the Cosmos, wrote, "If new universes are born inside black holes, then our universe might be selected for the kinds of physics that allow stars to collapse and form more black holes." That is life. Structure and complexity are not accidents, but evolutionary traits in a cosmic reproductive system. Universes that produce more black holes create more descendants. Could it be that our physical constants, the strength of gravity, the charge of the electron, the speed of light, are finely tuned, not by luck, but by inheritance? This might also help explain the mystery of entropy. Black holes possess enormous entropy, more than any other known structure in the universe, corresponding to the immense information they can contain. If a universe is born inside each black hole, then perhaps entropy is not a measure of disorder but of potential. Each collapse encodes the blueprint for a new cosmos within its horizon. And what of time? Inside a black hole, time slows to a crawl at the event horizon and ceases to have meaning at the singularity. Yet in our universe, time began at the Big Bang. Could it be that what seems like an ending from outside becomes a beginning from within? The birth of a universe, like a flame caught in a lantern, may blaze only because it is protected from view. Even more curiously, astronomers have noticed that galaxies appear to rotate with a preferred orientation, a large-scale asymmetry that challenges the principle of isotropy. If our universe had a directional imprint from a parent structure, a kind of angular momentum passed down from its formation, it might leave such a trace. The cosmic microwave background itself contains subtle anisotropies that whisper of something beyond randomness. Of course, this theory, while elegant, remains speculative. We cannot see beyond our cosmic horizon to verify if a larger universe enfolds us. Yet its allure lies not just in its explanatory power, but in its poetry. It restores humility to cosmology. It invites us to imagine our universe not as the whole of reality, but as one note in a much grander song. Perhaps the black holes we fear are not tombs, but gateways. Perhaps death in the language of the cosmos is just the turning of a page. And perhaps, just perhaps, we are living not in the aftermath of nothingness, but in the afterglow of a star that died so that we might exist. If that thought stirs something in you, a sense of awe, a flicker of curiosity, then the universe is doing its job. Keep wondering. Keep listening. For beyond the silence of collapse, there may be a symphony just beginning to play. What if the Big Bang was not the beginning of everything, but merely a heartbeat in a larger cosmic rhythm? What if the universe never truly began and never truly ends? For decades, the singularity, that infinitesimal point of infinite density and zero volume, has stood as the boundary of our understanding. A mathematical wall where physics breaks down and space-time ceases to make sense. But a different idea has been quietly forming in the shadows of general relativity, a whisper in the equations that suggests the universe may not have exploded from nothing, but rebounded from something before it. It's called torsion, a subtle twist in the fabric of space-time that Einstein's original theory overlooked, but which Élie Cartan introduced a century ago. In the Einstein-Cartan theory, torsion arises naturally when one considers not just mass and energy shaping space-time, but also the intrinsic spin of elementary particles, a fundamental property of all matter. According to this view, when matter becomes ultra-dense as it would in the moments approaching a black hole or the beginning of a universe, the spin of particles generates a repulsive force that counters gravity's collapse. It is not a stretch into nothingness, but a recoil, a cosmic bounce. Roger Penrose once said, "The Big Bang was not a unique beginning, but perhaps the result of an earlier ending." This notion aligns beautifully with the idea of a big bounce, a scenario in which our universe did not spring from an absolute singularity, but emerged from a previous contracting phase. Instead of being crushed into oblivion, the universe was pushed back by the torsional resistance of spinning particles, expanding once more into the form we now observe. Such a view is not mere speculation. It emerges naturally from a deeper reading of the geometry of space-time when torsion is included. Abhay Ashtekar, a leading figure in quantum gravity and loop quantum cosmology, has spoken often about how torsion-like effects could resolve singularities. Singularities are where the classical theory fails, he said, but quantum geometry could remove them altogether. The Einstein-Cartan theory isn't quantum gravity in itself, but it offers a compelling bridge between the classical and the quantum realms, one that does not require space-time to tear itself apart at the start of time. If the torsion-induced bounce is real, then the universe might be far older than we think, not in terms of our own era, but in cycles, eons of expansion and contraction, each new cosmos rising from the ashes of the last. The Big Bang then is not a spark from nothing, but the exhale after a cosmic inhalation. This breath-like rhythm has echoes in other theories too, from conformal cyclic cosmology to bouncing brain worlds, all suggesting that the singularity is not an edge, but a bridge. This vision carries emotional as well as scientific weight. For centuries, we've lived with the idea of a creation from void, an origin without precedent. But perhaps the universe doesn't need such abrupt beginnings. Perhaps nature prefers continuity, a graceful transition through thresholds rather than ruptures. In a universe with torsion, the extremes of density do not spell doom, but renewal. The spin that defines matter might be the very key that allows existence to persist, to return, to begin again. And what of the early expansion itself, that moment of incredible speed when the universe inflated beyond imagination in fractions of a second? Could torsion explain this too? In some extended models of Einstein-Cartan theory, the repulsive effect of torsion at high density could provide a natural mechanism for a rapid bounce-like inflation. It is not the same as the traditional inflationary field, but it speaks the same language: sudden release, stored tension unleashed into boundless growth. If so, the birth of our cosmos may not need exotic fields or unobserved particles, but only the overlooked twist in the matter we already know. Neil Turok, a prominent cosmologist, has said, "The biggest mistake we made was assuming the Big Bang was the beginning." The Einstein-Cartan theory may be the quiet reply to that mistake, offering a picture not of origin, but of evolution of a universe that remembers its past in the very spin of its particles. It invites us to consider that the cosmos is not a line with a start and end, but a circle, ever turning. As we look deeper into the early universe with tools like the James Webb Space Telescope, we may find patterns, chemical richness, structural complexity that hint at a longer history than we imagined, not just in time, but in memory. And in that memory, encoded in torsion, might lie the signature of a cosmos that has lived before and will live again. A universe not born in fire from nothing, but reborn in silence from something we're just beginning to understand. Is the universe truly the same in every direction? Or have we simply assumed so because we couldn't bear the alternative? What if all the galaxies, all the filaments and voids, even the afterglow of the Big Bang itself, were quietly whispering a cosmic alignment hidden in plain sight? An invisible thread stretching across the fabric of space-time, drawing the cosmos ever so slightly in a preferred direction. This unsettling possibility has a name: cosmic anisotropy, and it's more than just a mathematical quirk or statistical anomaly. It calls into question one of the most cherished assumptions in modern cosmology, the cosmological principle. The idea that the universe is homogeneous and isotropic when viewed on large enough scales. But what if that is no longer true? What if the universe is whispering to us through subtle patterns that something deeper, older, and stranger is at play? The first hints of this mystery came not from deep space telescopes, but from the sky itself. Specifically from the cosmic microwave background, the ancient light left over from the Big Bang. As early as the WMAP and Planck missions, cosmologists noticed peculiar alignments in the temperature fluctuations of the CMB. Not random noise, but something eerily structured, a pattern that appeared to align with the plane of our solar system. Something that should not happen if the universe were truly directionless. It was dubbed the axis of evil, a poetic name for a potentially paradigm-shattering anomaly. Professor George F. Starthew of the University of Cambridge once remarked, "If the axis of evil is real, it would be the most important discovery in cosmology since the cosmic microwave background itself." Others have warned against overinterpretation, yet the data lingers, persistent and uncanny. Even more recently, studies of galaxy spins suggest that vast numbers of galaxies seem to rotate in the same direction across enormous stretches of space, another potential sign of a preferred cosmic axis. In a random universe, spin should be distributed evenly, but the cosmos seems to favor one twist over another. If this alignment is real, it doesn't just contradict our models, it forces us to rethink our place in the universe. Because an anisotropic cosmos implies structure on scales beyond the observable horizon. It implies a deeper architecture of reality that our current theories cannot explain, not without invoking bold new physics or reconsidering the very shape and origin of the cosmos itself. Some theorists propose that this axis may be a remnant of primordial features, left imprinted during cosmic inflation, a brief moment after the Big Bang when space expanded faster than light itself. Others go even further, suggesting we might live in a bubble universe within a multiverse, and the anisotropy we observe is the scar of a collision with another bubble cosmos. Dr. Max Tegmark once suggested that if we saw evidence of such anisotropy, it would be like finding fingerprints on the glass wall of our universe. But perhaps the most poetic hypothesis comes from those who see this axis not as an error to be corrected, but as a clue to a deeper symmetry we don't yet understand. Just as Earth once believed itself the center of the cosmos until Copernicus shattered that illusion, so too may our current models be limited by assumptions born of limited vision. Perhaps the universe isn't an impartial sea of stars, but a living structure with orientation, with meaning. This doesn't mean the old models are wrong, only that they are incomplete. Like a map that outlines the continents but forgets the ocean's currents, or a melody missing its rhythm. Cosmic anisotropy suggests that the universe may not just be expanding, but unfolding, revealing its deeper geometry step by step as our tools grow sharper and our questions grow braver. And so we return to the silence between galaxies, the cold shadows of the CMB, the spiral arms of ancient galaxies all rotating with a quiet rhythm we never noticed before. Could it be that we are tracing the fingerprints of something vast and intentional? Some cosmic wind still echoing from creation itself. In the words of cosmologist John D. Barrow, there is no reason to expect the universe to be simple. And indeed, with each new observation, it becomes ever more profound, ever more personal. The axis is not merely a direction in space. It may be the first signpost on a road to understanding a universe far stranger than we dreamed. One that does not unfold equally in all directions, but spins its tail with a subtle twist. What if the ancient galaxies we now see glowing on the edge of the visible universe are not just distant in space but also strange in origin? What if their very existence whispers a truth we've long avoided, a truth that questions the nature of beginnings themselves? These galaxies should not be here, not so soon, not so massive. And yet they are. Their presence lingers like a riddle etched into the fabric of space-time. The James Webb Space Telescope has peeled back a layer of darkness and revealed a cosmos that bloomed earlier than expected. MOMZ-14 is one of these haunting anomalies, a compact galaxy that erupted with light just a few 100 million years after the Big Bang. It glows not faintly, but furiously, bursting with newborn stars and complex elements that should have taken much longer to form. Its mass rivals expectations and defies the traditional timeline. The question then arises, how could something so old be so evolved? Brian Cox once said, "Every time we look deeper into the cosmos, we are forced to admit how little we actually understand." That sentiment echoes louder now than ever before. Galaxies like MOMZ-14 should be rare, primitive, and struggling to ignite their first stars. But instead, they shimmer with complexity, rich in nitrogen and dust, lacking the supermassive black holes that most active galaxies harbor. They tell a story at odds with the models we've built. Perhaps the error lies not in the stars themselves, but in our tools for measuring them. Some astrophysicists have suggested that our understanding of the Milky Way's own rotational speed may be flawed. A miscalculation in our galactic motion could ripple into errors in estimating the redshifts of distant galaxies, an effect akin to mistaking the flow of time itself. If our baseline is skewed, then our distance ladder may wobble, and with it, our assumptions about how fast and far the early universe expanded. But what if the answer is not a mistake, but a new model entirely? Some physicists now speculate that our universe may not have exploded from nothing, but instead was born from the core of a black hole in a parent universe. This idea, Schwarzschild cosmology, proposes that every black hole could give birth to a new universe within. In this view, our cosmos is not the singularity at the center of everything, but rather the blossoming of something deeper, a rebound, a continuation. In such a scenario, time and space bend in unfamiliar ways. Gravity, under extreme conditions, twists and folds, and the laws we know give way to those we have not yet written. Galaxies forming too early may not be anomalies. They may be clues, echoes of a process not explosive but cyclical. A big bounce rather than a big bang. As physicist Nikodem Popovsky explains, a black hole in one universe can be the seed of a new strace universe. If this is true, the early galaxies we observe may not be outliers. They may be the children of a prior cosmos, carrying within them the chemical fingerprints of stars long gone from an older epoch. Their rapid formation, their chemical richness, and their defiance of simplicity could all point to this deeper heritage. Even Einstein, in the quiet of his late years, admitted he had never made peace with singularities. The idea that the universe could begin from a point of infinite density disturbed him. What if that discomfort was a clue? What if we were never meant to accept the singularity as a final answer, but as an invitation to think again? The ancient galaxies now shimmering in JWST's lens are not just scientific curiosities. They are messages in light. They tell us that time may not flow as we imagined, that beginnings may not be so absolute, that perhaps the fabric of the universe is stitched with cycles, not lines. This vision does not diminish us. It deepens our wonder. For if each black hole might carry within it a universe, then perhaps creation itself is a repeating miracle. Perhaps our own universe is but one flower in an eternal cosmic garden, blooming from the collapse of something else. And we, conscious creatures made of stardust and memory, are simply trying to remember how it all began. So the question remains, not just how galaxies like MOM Z14 formed so quickly, but what their existence is truly telling us. Are they errors in our models, or mirrors showing us that our models were always incomplete? Perhaps we stand at the edge of a new cosmology, one where time loops, where universes nest within one another, and where light from the past is really a signal from something deeper. The stars do not lie, but they do speak in a language we are only beginning to understand. And in their luminous silence lies the next great question of our place in it all. The discovery of ancient galaxies like MOM Z14 is not just a marvel of technology. It is a turning point in our understanding of cosmic history. These luminous sentinels from the edge of time are too massive, too complex, and too early to fit within the tidy scripts of our current models. They ask unsettling questions. Did stars live and die before we thought time even allowed it? Is our universe not a singular, explosive birth, but a cyclical dance within something greater? Perhaps the interior of a black hole in a parent cosmos. Whether the answer lies in flawed assumptions, hidden physics, or entirely new paradigms, one thing is clear: the universe is more imaginative than we ever gave it credit for. Every ancient light we capture pulls back the veil a little more, not just on the cosmos, but on ourselves. We stand humbled before the stars, reminded that knowledge is not the end, but the invitation. If MOM Z14 is a messenger, then perhaps its message is this: the story of the universe has chapters we have yet to read, and its opening line may not be the beginning, but rather once again,